In this video, we are going to talk about first-order difference equations. And first-order difference equations are the discrete analog of differential equations. So differential equations are for continuous processes. The example is a population that continuously grows, or maybe it's interest rate in a bank where you're compounding continuously. Whereas difference equations are for discrete processes. That would be something like in the bank example where you're compounding interest, maybe you only compound it at discrete intervals like yearly, or maybe it's monthly. And then for population, maybe these are species who propagate at regular intervals, such as a particular time in the calendar year, like spring, for example. And I just want to mention why whenever we study population models, we often look at equilibrium solutions, because this is where our population levels off or kind of is stable, or not necessarily stable, but where it levels off, and then we look at the stability of the equilibrium solution. So obviously, or maybe not obviously, but often when you're looking at a population, you want to know where the equilibriums are, and then you want to know stability. So this is no different. For these first order difference equations, we will be looking at equilibrium and then stability. We will be looking at only first order difference equations, and the formula for that is y n plus 1 equals f of n y. So what this means is at the nth plus 1 iteration, so maybe if you're talking about population, that's the nth plus 1 generation, or if you're talking about interest, the time period is n plus 1. Well, that's dependent both on yn, the previous generation, and also on n. This is considered first order because yn plus 1 only depends on the value yn, but not on earlier values, so we only have to look back one generation. A solution of the difference equation is a sequence of numbers, so you have, y, the population at different times, discrete points, and the equation is linear if f is a linear function of yn, so depending on what yn looks like. We're going to further narrow down which first order difference equations we will look at, and we will only look at first order difference equations that depend only on yn. So now yn plus 1 is equal to f of yn. So it only depends on the previous generation, and we have our initial conditions, y1 is equal to f of y naught. So we do something called iterating the difference to find our next term. Actually, it's not that hard, so I'll just look at it really quickly. So if y1 is equal to f of y naught, then the second iteration, y2, is f of, and then we have to plug in f of y naught, because this is f of y1. F of y naught is equal to y1, which is equal to f squared of y naught. The third iteration is f of y2, which is equal to f of y naught. So you can see we get that yn is equal to f n times of y naught. And then we are going to look at equilibrium solutions, and those are found by setting yn plus 1 equals to yn. Then our big analysis is going to be on linear first order difference equations, and we're going to use a population example. We will find the solution here, and we will talk about the stability of our equilibrium solutions. Then last, we will talk about nonlinear equations. And just as we had in differential equations, for difference equations, the linear equations we could solve. The nonlinear equations, many of them we cannot. We're going to restrict our attention only to the logistic difference equation, which looks like yn plus 1 equals rho yn times 1 minus yn over k. And if this looks familiar, it should, because this difference equation is the analog. It's totally analogous to the logistic differential equation, which looks like this: dy dt is equal to r y 1 minus k y over k. And for this, we're going to look at the equilibrium solutions and where it's stable. And when we look at the stability, this actually becomes interesting, because we're going to go towards unstable solutions. We're going to look at where things get chaotic. and literally we're going to look at chaotic solutions. So we're going to look at stability of equilibrium solutions. We're going to look at graphs and different visualizations, staircase and cobweb graphs, and then we'll move on and talk about bifurcations and chaotic solutions for nonlinear equations. So backing up, again, our first order difference equations, they are the discrete analog of the differential equations that we use for continuous processes. For example, a population growth may be described more accurately by a discrete model than by a continuous model. This is true, for example, in a species who propagate at regular intervals, such as particular times of the calendar year, in which case we would want a difference equation. We are going to focus on first-order difference equations, which look like yn plus 1 is equal to f. It's a function of n and the previous iteration. It's first order because yn plus 1 only depends on yn. It doesn't depend on like yn minus 1 or yn minus 2. So like y3 will only depend on y2. It will not depend on y2 and y1. The equation is linear if f is a function of yn. And the solution of the difference equation is a sequence of numbers, so kind of like the population at each of these intervals. And we're going to further restrict now what the equations we will look at from first-order difference equations to first-order difference equations that depend only on yn. So now our formula becomes yn plus 1 is equal to f of yn. And we'll have the initial condition y1 is equal to f of y0. And so we can iterate the difference. Y1 is equal to f of y0. So the second iteration, and I just kind of expanded and added an extra step. So y2, and this by this formula, is equal to f of y1, which is equal to, by this formula here, f of y0. This part is y1. So this is the f function applied twice to y0. Similarly, we get y3 is equal to f of y2, then that is equal to f of, plugging in what we had for y2, f of y0, that's the function f applied 3 times to y0. So the nth iteration is y0 is equal to f of y to the n minus 1, which is the function f applied n times to y0. And we are going, because these are population dynamics, we are going to look at equilibrium solutions and then study their stability. And if you recall, equilibrium solutions are where things kind of stay stable and things don't change. In other words, where yn is equal to f of yn. So one generation is equal to the previous generation. When we did differential equations, it's where dy dt was equal to 0. There was no change. And that, the idea of no change is encompassed or is captured right here. Yn is equal to f of yn. So that's solutions for which yn has the same value. And we find that by setting yn plus 1 equal to yn. So once you kind of understand the idea of equilibrium solution, this equation should come as no surprise. And first, we will study linear equations. Those are the easier ones, the ones that we can find a solution to. I have my formulas here for the general first-order difference equations, the one we're focusing on where yn plus 1 is a function of yn only, the previous year only, as well as when we iterate, our nth iteration, yn, is equal to f of yn minus 1, which is equal to f applied to y0 n times. And then also a note about our equilibrium solutions, yn plus 1 is equal to yn. We're looking at linear equations. So suppose a population of a given species for a given year, n plus 1, denoted by n plus 1, is a positive multiple rho of n of the previous year's population. So yn plus 1 equals rho n yn. And note that rho n may differ year to year, hence the little notation, the little n here, subscript n. The difference equation then can easily be solved by iteration. So y1 is equal to rho naught y0. Rho 2 is equal to rho 1, and then plugging in for y1, rho naught y0. And so rho n is equal to rho n minus 1, all your rows times y0. So this is a very easy equation to solve. Also, I'm going to just tell you that This should be a row, but the software I use to do these notes does not allow me a row, which is why I have P, because that's the thing that looks a lot like row. So sometimes I might be reading the equation, sometimes I'll say P because I'm reading the equation, but really it's row. And in your textbook and everyone else is going to say row. So note, although for a population problem, row n is intrinsically positive, the solutions we come up with is valid if row n is negative. Also note, row n equals 0 for some n, then y n plus 1 and all successive generations are all 0. In other words, the species has become extinct. Now, if the reproduction rate row n has the same value row for each n, then the difference equation simplifies to y n plus 1 is equal to row yn, and yn is equal to row raised to the nth power y naught. And there is an equilibrium solution for the initial value problem y equals 0, and the equilibrium solution is yn equals 0 for all n. So the limiting behavior as n approaches infinity, and you can look at this, and you can look as n approaches infinity, if rho is less than or equal to 1, you can see that this will make the solution smaller and smaller until eventually we reach 0, and this is asymptotically stable. Once you get there, you're not going to move away. If rho is equal to 1, just looking at this, then all of our solutions are going to equal to y naught. So that's also stable. However, if rho is greater than 1, you can see there's no limit. It's just going to keep growing. So the limit does not exist, and we are asymptotically unstable. One thing I find kind of amusing is this problem is so easy. A lot of people kind of miss it. I don't know. But, here we have our description described that yn is equal to, or yn plus 1 is equal to rho n times yn. So our solution when rho is constant is yn plus 1 is equal to rho yn, which gives us yn is equal to rho to the n, y naught. It's really that easy. And then really, to look at the behaviors, you just have to say what happens when n goes to infinity, if rho is less than 1, if rho is equal to 1, or rho is greater than 1. Don't make it more complicated than it is. That'll come. Complication will come soon. And look, here we have more complication. Actually, we're not going to call this complicated. We're going to call it sophisticated. We're adding more sophistication to our model. So sophisticated, that's what we're going for. So anyway, we're going to have, I just kind of moved up our information, our yn plus 1 is equal to rho n, yn, but we're sticking with the case where rho is constant. And we're going to add the effects of immigration or emigration, assuming a constant reproductive rate rho. So here it is, yn plus 1 is equal to rho yn plus bn. And bn, for this formula, can change. The emigration can change year to year. So we can iterate the difference of the equation, and we get y1 is equal to rho y naught plus b naught. Just setting n equals to 0, plugging in, we get y1. y2 now is equal to rho, and now I need y1 in here, so I plug y1 plus b1. And I get rho squared y naught plus rho b naught plus b1. y3 equals rho, now I plug in y2 here, and plus b2, and I get rho cubed y naught plus rho squared b naught plus rho b1 plus b squared, etc. So you can see the pattern. Every time you increase the generation, everyone increases by rho, except your last immigration, which hasn't propagated yet. So yn is going to be equal to rho to the n y naught. Those are the descendants of your original population. Rho n minus 1 b naught, these are the descendants of your first wave of immigration, and then all the other waves of immigration are here. And our formula can be written as rho to the n y naught plus the summation from j equals 0 to n minus 1, rho to the n minus 1 minus j times b of j. We are going to make another simplification. Yay, sophisticated and then now simple. So we will assume that bn is equal to b. In other words, that the immigration rate doesn't change year to year, and that it's not equal to 0. Now, if p also does not equal to 1, we can write our equation now as yn is equal to rho to the n y naught. That's, again, descendants of the original population, plus 1 minus rho to the n over 1 minus rho b. this is the form that we mostly see and will use, but we are going to rewrite this over here just so we can look at long-term behavior, looking for equilibriums and stability of those equilibriums. So yn is equal to rho n, y naught minus b over 1 minus rho plus b over 1 minus rho. So if we look at this, if the absolute value of rho is less than 1, this rho to the n is going to get smaller and smaller, making this term go to 0. So what we have is yn is going to approach b over 1 minus p. So this here is a stable equilibrium. Then next, we have if the absolute value of rho is greater than or equal to 1, then this will grow without bound. And also, if rho is equal to -1, this also will tend to grow without bound. So yn has no limits unless y naught is equal to b over 1 minus rho, just because that would give us 0. And then last, you can see that rho equals 1 is not a valid thing, so there's no equilibrium or stability here. And then again, I just wrote that the quantity b over 1 minus rho, for rho not equal 1, is an equilibrium solution and it is stable. And a comment, we talked about this as a population of, I don't know, some species, and this was our solution. But this same model provides a framework for solving many problems of financial character, because you can think of your population as a population of money. So for such problems, yn is the account balance of the nth time period, pn is equal to 1 plus rn, where rn is the interest rate for that period, and bn is the amount deposited or withdrawn. And here I have our general solution for this linear difference equation, where the difference equation looks like yn plus 1 is equal to p rho yn plus bn, the immigration, rho being the growth rate, and here is our solution for that difference equation. Now we can apply it to a specific application or example. A recent college graduate takes out a $10,000 loan to purchase a car. If the interest rate is 12%, what monthly payment is required to pay off the loan in 4 years? By the way, our time shouldn't be in years but in months, so this is 48 months. I have my notes here about applying our model to a financial model, and our solution yn, that's how much money that is owed at that time, is equal to rho n y naught plus 1 minus rho n over 1 minus rho b. So yn is the amount we owe, and at the beginning y naught is equal to 10,000. Our growth rate is 1.01 per month. Remember, this is per month. It's 12% per year, so we divide that to 1% per month. And n is equal to 48 months. We want to pay it off in 4 years. And here we have our equation, y of 48. We want to pay this off in 48 years. So after 48 months. After 48 months, we want to have 0 left in the amount owed. Here, while we're waiting to pay it off, this amount that we borrowed is accumulating interest at the rate of 1.01 to the 48. And again, the 1.01 comes from the 12% annual, which is 1% monthly. So this is, if we weren't paying anything off, we would just owe more money. But here, we're going to be paying things off. So we're going to migrate money out, the immigration. So we want to know how fast or what rate b we need to immigrate out. And then we multiply by our 1 minus rho to the 48 over 1 minus rho. Solving this equation for b, we get b is equal to $263 per month. And just to kind of look at this, $263, 48 months, we're going to end up paying $12,624. That's $2,624 of interest. Okay, so we finished up what we wanted to say about linear equations. Now we're going to look at the nonlinear equations, which naturally is more sophisticated. As I had mentioned, when we look at our nonlinear difference equations, we are going to focus on the logistic difference equation, which I've written twice for I don't know why. But here's our logistic difference equation. Yn plus 1 is equal to rho yn times 1 minus yn over k. And I had also mentioned before this might look familiar because it's analogous to the logistic differential equation, which looks like dy dt is equal to ry times 1 minus y over k. You know, the change here corresponds to yn plus 1. The rho and the r are kind of a rate of growth. We have our yn and then yn over k, where k was carrying capacity. To look at our logistic difference equation, we're going to be looking at where we have stable equilibriums. The first thing we are going to do is scale our variable. Then we're going to find or look for equilibrium solutions by setting our mu n plus 1 equals mu n. And the mu here is because we scaled. We'll go through it in the next slides. And then last, we're going to look at the stability of our equilibrium solutions. And that will lead us to some discussions about how we can visualize and graph these solutions, because our more complicated solutions will lead us to chaotic solutions. By the way, I apologize for the vacuuming in the background, but you know, we have to have vacuuming going on, and we have to have differential equations going on. So our first step is to scale our variable. First, I have rewritten our difference equation. Yn plus 1 is equal to rho yn 1 minus yn over k. I want to scale, so I'm going to use mu n is equal to yn over k. So I'm going to scale our variable by k. This equation here will give us yn is equal to mu n times k. So plugging into here, I'm going to have mu n plus 1 times k. Remember, because now if I want yn plus 1, I have to have my mu n plus 1 times k. I have to multiply by k, is equal to rho, and then plugging in for yn, I have mu n times k times 1 minus, and here I can just plug in mu n. So what that is going to give me is mu n plus 1 is equal to rho mu n times 1 minus mu n. Now that we scaled our variables and we simplified our equation here, which is the same equation we had on our last slide, and I rewrote here, mu n plus 1 is equal to rho mu n times 1 minus mu n. Now we're ready to find the equilibrium solutions by setting mu n plus 1 equal to mu n. Subtracting mu n on the other side and also multiplying this out, I'll get rho mu n minus rho mu n squared minus mu n, and that'll equal 0. Manipulating this, I have rho mu n squared plus mu n 1 minus rho is equal to mu n times mu n rho plus 1 minus rho is equal to 0. So since we have two factors that equal 0, it must mean one of these factors equals 0. So either mu n equals 0, or setting this equal to 0, I have mu n rho plus 1 minus rho is equal to 0. It gives me mu n is equal to rho minus 1 over rho. Now that we have found our equilibrium solutions, which I have written here, mu n equals 0 or mu n equals rho minus 1 over rho, we need to know, are these equilibrium solutions stable? And I'll repeat kind of what we had talked about before about stable equilibrium solutions. So equilibrium, you know, they're nice and peaceful, nothing changes, it's very peaceful, nothing happens, nothing's going on. But they're kind of like, a little bit like a black hole, in that, although black holes don't sound peaceful, but just go with me on this one. They're like a black hole in that once solutions or numbers get close to the equilibrium, they sort of get drawn in, and then they end up staying at the equilibrium. It's like very enticing. Things get drawn into the equilibrium, and then they're caught and captured, and they stay at that equilibrium value. Whereas if you're unstable, then numbers can get close to that equilibrium, but then no, it can get, you know, just really, really close. So it's just infinitesimally away, and it can still escape and go off in some other direction and go and grow unbounded. It can do whatever it wants. So the idea when you look at equilibrium solutions, you can also look and determine stability from an initial condition and say, well, let's say I am initially very close to the equilibrium. Do the numbers start to get drawn into the equilibrium? Do they stay near or do they veer off? So we're going to consider our first equilibrium point, mu n equals 0. And when we consider mu n equals 0, that means mu n squared is much smaller than mu n, right? Because mu n is small, and when you square a small number less than 1, it gets even smaller. So we're going to approximate mu n plus 1 with just the row mu n portion. We're going to ignore this part where we have the mu n squared. And what that allows us to do is look at this, because now we're linear. We no longer have the mu n squared terms. We're linear. So then we can go back, because before we looked at the nonlinear equations, we looked at the linear equations and see what we had learned from our linear equations. In particular, we learned that the equation or the equilibrium would be stable if the absolute value of rho is less than 1. And just to review for your benefit what we saw for linear equations, here is our previous problem and previous slide with linear equations, where we found the solution here, and then we looked at the solution, and we talked about and we rewrote it in this form so we could look at the stability of solutions, and we found if the absolute value of rho is less than 1, then this gets to be as n gets large, this will get very small, so this term will go to 0, and our solution will approach b over 1 minus rho. Whereas if rho is greater than 1, then this term gets really large, or if rho is equal to minus 1, the term gets very large, and yn has no limit, so it is unstable. And also rho equals 1 is just not allowed because of this 1 minus rho on the bottom. So again, the point is if the absolute value of rho is less than or equal to 1, then our solution will approach b over 1 minus rho, and it's a stable equilibrium. And applying that to our current nonlinear equation, which then we reduce to a linear equation, we will say that mu of n equals 0 is stable if rho is between -1 and 1. Now we can look at our next equilibrium point, which is mu n equals rho minus 1 over rho, and we're going to consider the solutions near mu n. So we're going to look very close to our equilibrium point, but we're going to perturb the solution by a small amount, v of n. So here I have mu n is equal to our rho minus 1 over rho, and I'm going to add this very small number vn to it, and we're going to see what happens to the solution. We're going to plug it into our equation, our solution, which is mu n plus 1 is equal to rho mu n times 1 minus mu n, and that will give us mu n plus 1 rho times, and now we plug in our rho minus 1 over rho plus vn here for mu n. And so this is what this is, rho times rho minus 1 over rho plus vn minus, and then multiplying this, I'm going to have rho minus mu n squared. So I take this mu n, which is rho minus 1 over rho plus vn squared. Now algebraically, I'm just going to factor out the rho, and I get this expression here. The rest of all this is algebra, which you are welcome to follow, until I get my mu n plus 1 is equal to, and then simplifying this expression, I get mu minus 1 over rho, rho minus 1 over rho plus v sub n times minus rho plus 2 minus rho v sub n squared. And now I'm going to take a moment at my mu n is equal to rho minus 1 over rho plus vn, which means our mu n plus 1 is equal to rho minus 1 over rho plus vn plus 1, which means this mu n plus 1 minus rho minus 1 over rho is going to equal to vn plus 1. Again, this vn plus 1 is mu n minus 1 minus this rho minus 1 over rho, and that's exactly what we have here. So I have vn plus 1 is equal to the rest of this equation, which is Vn times 2 minus rho Vn squared. And I've kind of summarized things here. I was considering solutions near mu of n is equal to rho minus 1 over rho. I perturbed this solution by a small amount, Vn. And what I got is Vn plus 1 is equal to Vn times 2 minus rho Vn squared. Since Vn is really very small, we're going to drop this term here. And by doing so, we get a linear equation. So Vn plus 1 is equal to Vn times 2 minus rho. And this is the same trick we did for mu n equals 0. So here I have my linear equation. Vn plus 1 is equal to Vn times 2 minus rho plus 0, just because again, when we looked at our linear equations, this 0 represents Bn, it equals Bn, and so if rho, absolute value of rho is less than 1, then Yn approaches B over 1 minus rho. In this case, B is equal to 0, so that means in this case we have Yn, we have rho is 2 minus rho is less than 1, so that means Vn approaches B over 1 minus rho equals 0 when 2 minus rho is between negative 1 and 1. In other words, when negative rho is between negative 3 and 1, or when rho is between 1 and 3. Then Vn approaches 0 as n approaches infinity. So this is also a stable solution when rho is between 1 and 3. And now we have answered all three questions. We have found our equation. We scaled our variable to simplify our equation. This is not the solution. We just simplified our equation so that we could find our equilibrium solutions, and we found two stable equilibrium solutions. So we've, from the equilibrium solutions, we've learned a lot about this population. We learned to what number this population will tend to go to. But now we're going to take another look at this graphically and see what else we can learn. And remember, mu n is just our Yn, our population, but it's been scaled by k. So here we can see our population versus n. So as the years or whatever time period n represents, this is our population, mu n. And this is for rho equals 0.8. And remember, we said that when rho is between negative 1 and 1, which 0.8 is, we expect our equilibrium solution to be 0. So you can see the populations going down and kind of approaching 0. Here we have rho is equal to 1.5. In this case, we're in this part of our equilibrium. So we're expecting to approach here. The mu n is equal to 0.5 over 1.5, just subtracting rho minus 1 over rho, which is equal to 1/3. And this is exactly what happens with this graph. Here we have rho is equal to 2.8, again in this portion of our, where we expect the equilibrium solution. So we expect the equilibrium to be at rho minus 1 over rho. So here I have the rho minus 1 is 1.8 over rho, which is approximately 0.6429. So somewhere around here, we can see that we start to kind of hover around the equilibrium solution and sort of converging, but we're kind of oscillating around it as we converge. There is a second type of graph called either a staircase, because of this staircase look, or a cobweb graph because of this kind of cobwebby look, that also illustrates this idea of approaching a equilibrium and different ways of doing it, staircase or cobweb. And what we do is first we graph our solution curve. So our y equals rho x 1 minus x. And here, instead of, so our y is our yn plus 1, and our x is our yn. And we did that because, we're kind of graphing y versus x. And then, of course, x is also yn scaled. So we have y equals rho x times 1 minus x. So we get, if rho is equal to 0.8, we get this parabola here. If rho is equal to 1.5, we have this parabola, and rho equals 2.8, we've got this parabola here. And we have the parabola, and then we also look at the graph y equals x for reasons that will become clear in just a moment. The idea now is that if we start at an initial population, or x equals 0.3, then we plug it in to get our first initial value of y. So this is this point on our solution curve. Y equals rho 0.3 times 1 minus 0.3. We get this point here. Now we plug, so this is the y coordinate, whatever this is, something a little like, I don't know, let's just say it's 1.8. So y is equal to 1.8. So our 1.8 becomes our new x value. So we move over to x equals y. So this is our x value. It should be kind of like 1.8. Looks more like 2, but just ignore my graphing capabilities and say it's whatever y value is, that's where we are here on x. And then we plug in x into our equation, and we land on this portion of the graph, of our solution curve. Now we take this value of y, we make it our new x value, we plug it in, and we land on this portion of our solution graph. And we keep doing that. So we have this staircase graph that kind of is, this is how we approach our equilibrium point. If we have rho equals 1.5, and let's just choose a different initial value, which is 0.85, somewhere around here. We plug in 0.85 in for x, and we get this value of y. So this is our first point on our solution curve. But now our value of y is what? Somewhere around, I don't know, 2.8 or something. So we come over here, and we find 2.8 on the x value, and then we plug it into our equation, and we get our next y point. And then again, we come and find our next x point, plug it in, and get our next solution point. And we have this other staircase. This is how we approach the equilibrium this way. Over here, for rho equals 2.8, this is the approach, if you recall. When we go towards equilibrium, we kind of oscillate around the equilibrium point. To remind you what that looked like, here we have the n versus un, and you recall we start to oscillate around this equilibrium point of 1.8 over 2.8. What that looks like in our staircase slash cobweb kind of graphs is if rho equals 2.8, let's say we start again at our initial condition equals 0.3. So what we do is we go up, we plug in 0.3 into our equation, we get the solution y equals whatever this number is, somewhere around 0.5. Then we use 0.5 as our next x, so that's where y and x are both equal to 0.5. So we plug in 0.5 as our next x value to put in y, and we get our next solution, which is over here at y. Then we come over here to find our next x value, plug in, and we come down to this solution point. We go over, and then at this point we come and find our next solution. We go over, we find our next solution, and you can see we have this kind of cobweb spiral design, and that's what we get when we're oscillating around the stability point. In the cobweb design, we're kind of circling around the equilibrium point. And here I have a description of this cobweb staircase diagram. So this piecewise linear graph, these staircases or these cobwebs in red, consisting of successive vertical and horizontal line segments, sometimes called a stair-step or cobweb diagram, represents the solution sequence. The sequence starts at a point mu naught on the x-axis. So for example, here, here, or here. The vertical line segment drawn upwards to the parabola at mu naught corresponds to the calculation of mu1 is equal to rho mu naught 1 minus mu naught. So here up to the parabola. This value is then transferred from the y-axis to the x-axis because that y value becomes our new x. And this step is represented by the horizontal line segment from the parabola to the line y equals x. So here, once we have our solution, it becomes our new value of x. And then this process is repeated over and over. So we have our new x value, we calculate our y value according to the equation, and then we transfer it over. Again, this is just another way we can view how we can approach these equilibriums. And now that you've been given the examples and explanation, certainly you could also draw one of these. Another way of looking at this, and this will get us into discussions of what a chaotic solution will look like. So our difference equation, which is here, also rewritten here, rescaled here, has two equilibrium solutions. Mu n equals 0, which is asymptotically stable when rho is between -1 and 1. And our second equilibrium solution, mu n, is equal to rho minus 1 over rho, which is asymptotically stable when rho is between 1 and 3. And when rho equals 1, the equilibrium solutions coincide at mu equals 0, and the solutions can be shown to be asymptotically stable. So we're going to graph this, the parameter p versus mu. So equilibrium solutions are shown. Intervals in which each one is asymptotically stable are indicated by solid portions of the curve. And then when they are not, when they're unstable, they'll be dotted lines. So here we have the graph of our second solution. Mu equals rho minus 1 over rho. So you can see when rho, it's this curve here. When rho is less than 1, it is unstable, so that's the dotted line. At rho equals 1, it becomes stable, and then at rho equals 3, it becomes unstable again. Then here we have our graph of mu equals 0, and you can see when rho is less than 1, we have a stable solution. Once we hit 1, it becomes unstable, hence the dotted line, and it continues to be unstable after rho equals 3. So intervals in which each one is asymptotic stable are indicated by solid portions of the curve. I talked about that. There's an exchange of stability from one equilibrium solution to the other at rho equals 1, right here. That's where this solution becomes stable and this solution becomes unstable. And for rho equals greater than 3, neither equilibrium solutions is stable. Next, we're going to look at rho greater than 3, where, remember, we don't have any stable equilibriums anymore. So for rho a little bit greater than 3, we'll see the sequence mu of n oscillates back and forth between two distinct values. And what we'll see as we increase in this logistic differential equation, what we'll see as rho increases, we're going to have it oscillate back and forth between more and more values until essentially not only are we just not stable, we don't have a stable equilibrium, we sort of devolve into chaos. So let's see what that looks like. And what we say is rho somewhat greater than 3, so we're looking at rho equals 3.2 here. The sequence mu n approaches a steady oscillation of period 2, and by period 2 we mean that un oscillates back and forth between two distinct values. That's what the period 2 is. So here we see that mu is going along, and then somewhere it starts to oscillate between 0.7995 and 0.5130. If we looked at the Cobweb diagram, then starting with an initial condition 0.3, we would get to 0.7995, and then we plug that in as our x, and then we can see we come down to our solution curve, and that will give us 0.5130. When we go over across to find our next, to let x equal our last y, we're back at 0.5130, so we go back up and we're at 0.795, we go over and we're kind of in this closed loop, and that's what this oscillation looks like. At about rho equals 3.5, each state in the oscillation of period 2 separates into two distinct states, and the solution becomes periodic with period 4. And as p increases further, periodic solutions of period 8, 16, etc. appear. So here we have at rho equals 3.5, we have this one oscillation between something greater than 0.8 and somewhere around 0.4. Here's our 0.8, 0.4, 0.8, 0.4, 0.8, 0.4. But inside we have this smaller oscillation too, our original one, which is like 0.77 and 5.1, 0.77, 5.1. So we have two periods in here. So the transition from solutions with one period to solutions with a new period that occurs at a certain parameter value is called a bifurcation. So somewhere around 3.5, there's this bifurcation where we go from period of 2 to period of 4. The value of the parameter where the bifurcation occurs is called the bifurcation value of the parameter. When oscillations vary so that its fine structure becomes unpredictable, the term chaotic is used to describe the situation. So we could keep bifurcating until finally we have so many different, our signal just becomes where it's impossible to identify periodic solutions. It almost looks unpredictable. It's chaotic if we continue to bifurcate. One of the features of a chaotic solution is the extreme sensitivity to initial conditions. So that what that means is, if you have an experiment and you start at some initial condition, say mu is equal to, or your first value is equal to 0.3, for example, then you want to replicate that experiment, and maybe you have just almost nearly the identical conditions, but not quite. So maybe mu is equal to 0.99999 or 0.2999999. So really close to 0.3, but not quite. So you'd expect, if you have a nice behaved function, that your outcome should be roughly equal. But in a chaotic kind of situation, what that means is even though you have something incredibly close in your starting conditions, that you can get a wildly different outcome at the end. So that's what's considered chaotic. It makes it really impossible then later to predict things, because the only way you can predict something is if you start with the exact same initial condition. Because if you're a little bit off, you'll get something wildly different than what your model or what you've experienced before. So that's why it's called chaotic. And again, the feature is that the solutions are extremely sensitive to the initial condition. If you want to be able to replicate experiments, you have to have the exact condition. If you want to somehow predict things based on past experiments, you have to basically have the exact same conditions, because having conditions that are close is not good enough in a chaotic system. And chaotic solutions are much more common than was expected at first, and may be part of an investigation of a wide range of phenomena. The butterfly flaps its wings, and I don't know what the rest of it is. But that's the idea of a chaotic solution. And here we've seen that with this, the logistic difference equation, we're getting bifurcation after bifurcation until finally we'll hit a chaotic solution. And remember, we're starting to see these bifurcations at rho equals 3.5. If we continue to maybe rho equals something near 4, we probably have a great number of bifurcations, and then we'll start to see chaotic behavior. Okay, reviewing what we have looked at in this video, we looked at first order difference equations. And again, they're the discrete analog of the differential equation for a continuous process. So in other words, if we, it's like population growth, but maybe we have population growth that's described more accurately by a discrete model, such as when a species propagate at regular intervals, like a certain time of the calendar year, say spring. So instead of a differential equation, we have a difference equation where yn plus 1, so the future population, is equal to a function of n plus our current population. It's first order because yn plus 1 only depends on yn, but nothing earlier. So not yn minus 1 or yn minus 2. So if you want to predict what the population is on year 3 or yn equals 3, you only need to know about yn equals 2. You don't need to look back to yn equals 1. A solution of the difference equation is a sequence of numbers, so you get the population on different years. And the equation is linear if f is a linear function of yn. We focused on first order difference equations that depend only on yn, so we drop the n here. And we have yn plus 1 is equal to f of yn, with initial condition y1 is equal to f of y naught. Then to solve, to figure out what yn is, we just kind of did this iteratively. So y1 would be equal to f, and then we plug in y naught. The second one, y2, is equal to f of y1, which is equal to f of y naught, which is y naught with f applied twice. The third iteration is y3 is equal to f applied 3 times to y naught, and the nth iteration is f applied n times to y naught. We looked at equilibrium solutions, which are really important for populations because we want to know how the population will level out. And the way we found equilibrium solutions is setting yn plus 1 equals yn. And remember, because equilibrium solutions are when the population has reached an equilibrium and no longer changing. So in other words, each consecutive year is just equal to the past year. We looked at linear equations. So we had, this was our solution to our linear equation, that yn is equal to pn y naught plus, and then we introduced immigration or emigration as people can move in and out of the population, 1 minus rho n, 1 minus over 1 minus rho. And we said we would have stable equilibriums if the absolute value of rho is less than 1. And then our equilibrium will approach B, our immigration, over 1 minus rho. Otherwise, we have unstable equilibriums. Then we went on and looked at nonlinear equations. And we were we restricted our attention to the logistic difference equation, yn plus 1 is equal to rho yn times 1 minus yn over k, which is this difference equation is the analog to the logistic differential equation, which we saw in the last chapter or last video. And what we did to analyze these solutions is we scaled our variable first to simplify our equation. We found the equilibrium solutions, and then we looked to see if the equilibrium solutions were stable. And this is what we found for the logistic difference equation, that we have mu n is equal to 0 is a stable solution for rho equals negative 1 to 1, and mu n is equal to rho minus 1 over rho is a stable solution for rho between 1 and 3. And remember, we had done some simplifications where we're looking at it as a linear system by the time we simplified things. And so we could also use this equation that our second point of stability is rho minus 1 over rho. Then the next thing we did is we looked at some graphs, staircase and cobweb graphs, to kind of further enhance our understanding of what was going on. And then we went on to bifurcations and chaotic solutions, and we defined what it was to be chaotic, which was to have, among other, well, not necessarily a formal definition, but we said that one of the characteristics of a chaotic solution is that there's extreme sensitivity to initial conditions. So in other words, 2 points that start off exactly the same can end up very different. So in other words, the initial conditions, extreme sensitivity means if you want something to end up in the same place as like your original experiment, you essentially have to have the exact same initial condition. You can't have any variability because there's so much sensitivity. A little bit of variability will send you off in a totally different direction. Okay, that's it for this video. Thank you for watching.